Hi everyone, this is Jesse here from SkyCiv, and today I want to do a design example looking at how we can design a timber member to the Australian standards using the Quick Design module. So the first thing I want to do from the dashboard here is I want to open up the Quick Design software. I'm going to go to the Australian Standards tab and then type in timber to find the sought after. So I'm after this one, timber design to the AS 1720s. When I open that up, what we're going to get here is our inputs on the left, a section for our report in the center, and a section for our outputs on the right. I'll run the calculator with the default values so you can see what that looks like. We've got our input, our summary here, in the center of our calculations. And we can see on the right here, we've got our outputs, which is our member capacities and our utilizations. We can see with this default setting, everything's green, everything's passing. Now what I want to do is I want to go through these inputs and I want to update these for the design example we're going to do today. This design example, it's example 6.2 from the HB 108 textbook. And this example is for some stud framing, which is under both compression leading and bending in the major axis. So the design example is one of the only ones in this textbook for combined actions. That's why I want to do it today. Rather than doing just bending or compression, we'll kind of do everything all in this one example. So what we're going to do is we can give this member a name. For our own reference, this would show in our report. I'm just going to put example 6.2 HB 108. And we're just going to slowly go through the inputs that we get from this design example. So the first thing we know is that we have F5 Cypress pine, which is unseasoned. So we can put in our property of sawn timber, our grade as F5, treatment as unseasoned, and is pine. So we have softwood here. The section properties are given as 100 by 50. And I can type that in 100 by 50, but we can see it's not a typical section. So I'm just going to go to custom and type this in manually, 100 by 50. And we can see up top here, we've got what our section looks like, 100 by 50. For our loading and duration, we have this this setting here. Are we looking at bending loads, axial loads, or bending and axial? This just hides like inputs we need, so it just makes everything simpler for us going forward. In our case, though, we're going to look at bending and axial, and we're just going to get all the inputs. But if we were, just looking at axial, this would make our inputs quite a bit shorter. So for bending and axial, we put that in. The load duration that we're going to be looking at is for a 5-second ring load. And for our member, we have a primary member. We're looking at a building which is a resort, so it's not a house. And then from this, we're going to get our 5-factor, and we'll see that in your report. Bolt holes are only relevant when we're designing a member in tension. If we have compression, the compression force just goes through the bolt itself. So this doesn't actually matter, and we're not given anything. So we just leave that as 0. For moisture and temperature, we can see a note here that for seasoned timber, typically has an MC less than, moisture content that is less than 15%. And for unseasoned, it would be greater than 25%. So if we don't want this to affect our K4 factor, for unseasoned timber, I'm just going to put 25, which will be conservative. For load sharing, we do have load sharing in the major axis. The reason we only have either major or minor, not both at once, is because to have both at once, you'd have this weird grid of elements. Usually you're just going to have elements lined up in the one plane. Like if it's floor joist, they'd be lined up in the direction of your floor. You're not going to have them through your entire above ground as well, basically. So in our case, we just have our wall and our studs are aligned so that they share loads about the major axis. In this design example, we're directly given the factor that comes from this load sharing value, and back calculate to find out if we put this value as 4, this end member value, which means that we have 4 discretely spaced members. If this is 4, we'll get the value that they've given in the design example. For restraints, the restraint that we have is we have noggins at the mid-height, first of all. We have obviously our connections at the end of the member. But then we also have cladding on either face of the bore. And what that means is we're going to have restraint on both the compression and tension edge, and we're going to have that as the continuous restraint. So we're going to have that as a continuous restraint, and we're going to have this G13 factor taken from table 3.2 as a value which is for studs in light framing, which is 0.9. The total height of the wall is quite a typical value of 2700 millimeters. So we can put that in. Next, we come to this LAY and this LAZ value, and we can kind of see on this diagram here what this is referring to. So this is referring to the spacing between our restraints to stop our member from buckling in either of the axis directions. So for LAY, we have our cladding effectively stopping any buckling in this direction. So for this, we can put just a more small value, which just means, yeah, a member's not going to buckle. And for buckling in Z, we don't effectively have anything, so we're just going to put the full height of the member for this value. Not going to worry about bearing for this example. And then for design forces, that's just coming from this example. And to write this in, we have 0.63 kilonewtons for our moment about Z, 0 for our moment about Y, 0 for our shear forces, and for our axial load, we have positive being compression and negative being tension. We have a value of 1.30 kilonewtons. So in the design example, they also give us two different compression loads, but the one we're going to be inputting is the one related to this 5-second load in this moment, which comes from the wind force on the wall. So these are both associated with the 5-second load duration. And if you wanted to do the other load case, we could put this to 0. This is 1.35, and we change the load duration. So that's all the values that we needed. I'm going to run this, but I'm going to just make one note that there's a small mistake in the example, which means that I'm just going to change this to be up by 1 millimeter. So now we can look at our design report. We've got our summary of everything we've put in. So if you print out this report and give it to someone, they'll see exactly how we've come up with all our numbers, and that someone else could recreate this example. Now, the first thing we do is for unseasoned timber, we reduce the cross section. We don't do this for seasoned timber, but for unseasoned timber, we have different design like depth and width that we use. The design example just made a mistake and it's deducted 3 millimeters instead of 4 millimeters for this example. So that's why I've just put the extra 1 mil there. And now with this, we're just going to get pretty much the exact same values everywhere, except for some minor rounding differences. Like, for example, they use 45/60 for the cross-sectional area. But as we go through this design example, we get the exact same values as the design example. Now, the way we've presented this is we've got all our cross-sectional properties that relate to, this D by B arrangement. These are just coming from typical formulas. And then we have our material properties, which is related to the strength of our timber. This is getting pulled from tables inside the standard. And in some cases, we have our material constant, which come from these formulas that were just shown down here, just to show everything and where it's all come from. But yeah, this is just presented quite similar to how the standard has it, just in a table, where we've presented this all at the start, so all this information is lumped together and quite easy for you to read through. Now, as we go through the calculations, we first of all get our factors that we need. So, for example, for our fire reduction factor, we first, we just basically run through all the inputs that we have. So we have a primary member in not a house. It means we have a category 2 for our table that we use for the capacity factor. And for F5 some timber, we get 5, 0.7. And we can slowly continue to run down this design example. So for our 5-second load duration, we have K1 of 1. We have a K4 of 1, like I said before, we've just set this up to be the conservative value of 25% to get a K4 of 1. If we wanted to, it would probably be likely that this value would be less than 25. In that case, we'd get a K4 which is greater than 1 if we wanted to increase our capacity. For our K6 factor, we are at a location, so this is kind of location dependent. We're at a location where K6 would be 1, but we also have unseasoned timber, which means we don't even need to worry about allocation. This K6 is just going to be 1 anyways. Our factor for strength sharing is going to be different in the different directions. So in our case, we said we've only got strength sharing in our major axis direction. So in our minor axis direction, we've just got K9 equals 1. And in our major axis, we get K9 equals to 1.19, which was given in the design example. And as we go through our calculations, we can get our K12 values. So these values, K12, there's both the K12 for bending and for compression, which are different. But the meaning of it is the reduction in capacity due to buckling. So the way that buckling happens for bending and compression is slightly different. So we get slightly different calculations. And for bending about the y-axis, we don't have any buckling. There's no reduction required. So K12 equals to 1. I can continue to go through this calculation. And we did like these calculations related to buckling still. So in this case, we've got our continuous strain on the compression edge, which basically just results in a K12 of 1 as well. We're not going to get buckling. And for compression, the K12 factor is going to be related to the LAY G13 and these other parameters here, which we've also input. And in this case, we're still going to get a buckling value of 1, which means it's not happening in the Y direction, but when we get to the Z direction, finally we're going to get an actual reduction. So here we can see that we have this S value of 25.05 times that by our material constant, which we calculated at the start of this report, we get a value of 26.8. When we put that all together, we can calculate K12 as 0.279. I think this is slightly different to the design example. This is quite sensitive, this value, to this number here, and I think they've just got a slight rounding difference to get. I think they got 26.9 and made this slightly different, this value. And yeah, we finally put all these values together and we get a capacity of 35 kilonewtons for compression when we talk about buckling in the Y direction. And in the Z direction, we get a 9.7 kilonewton capacity, which is obviously more critical. So we take the 9.7 kilonewtons capacity as our compression capacity for the member, and we get the utilization. We don't need to worry about shear in this design example. And for bending strength, we also put all the properties we got together to get a capacity of 0.857 kilonewton meters and utilization of 0.74. For minor bending, again, we don't have forces in the minor bending direction, so we're just going to get a utilization of 0, so not too much. And finally, we need to combine the bending and compression utilizations together and see how do these work together to affect the overall utilization of the member when we combine these together. And we have these two different criteria, these two different formula, and checking both, we can see both utilizations are okay. These values are slightly different to the design example values because they've changed this value to 0.35, but actually it should be to 1.35, but actually it should be 1.3. So these numbers here are correct. And then finally, on our last page, we get just a summary, the same summary that we have on the right here. So if we wanted to get that report, we could just click PDF report, and we get this page, this PDF page that we'll share with our colleagues or our clients, so they can have a copy of this report too. So that's everything for this design example. We could see how we put in those inputs, put the report, and assess the output utilizations to see if everything's passing, our design's okay. If you have any questions about this design example or any questions about the tool in general, you can drop us a message here in the chat box, and we'll get back to you as soon as we can. Otherwise, I just recommend having a play around with the tool, having a play around with the Quick Design Library in general, and letting us know if you have any questions. Thank you. Bye.